Hello and welcome. Have you ever stirred sugar into your tea? Opened a soda bottle and watched the bubbles rise? Or noticed that salt dissolves instantly in water, but oil doesn't? If you've seen or done any of that, congratulations, you've already worked with solutions in your daily life. In chemistry, understanding solutions is a foundational concept that you will encounter again and again, whether you're studying biology, physics, or engineering. In this lesson, we'll explore what a solution is, what its components are, and how we classify different types of solutions based on various criteria. Let's begin. In chemistry, a solution is defined as a homogeneous mixture of two or more substances. Now, let's pause there. What does homogeneous mean? It means that the composition of the mixture is the same throughout. You can't see separate parts. Everything looks uniform, just like salt water or air. No matter how closely you look, the salt and water appear as one phase. Solutions of this type, where the solute particles are on the molecular scale and cannot be filtered out or seen under a microscope, are known as true solutions or molecular solutions. So, once a solution forms, the solute cannot be separated by filtration. It also doesn't scatter light, that's why a laser beam passes right through salt water without glowing, unlike colloids. Every solution has two main components, the solute and the solvent. The solvent is the substance that is present in the larger quantity. It's the medium in which the solute dissolves. The solute, on the other hand, is the substance that is present in the smaller amount and gets dissolved. Let's look at some examples. In a sugar solution, sugar is the solute and water is the solvent. In dental amalgam, zinc acts as the solute and mercury as the solvent. In seawater, oxygen is the solute dissolved in water, which is the solvent. Typically, the state of the solvent, solid, liquid, or gas determines the overall state of the solution. Let's explore the 9 types of solutions based on the physical states of solute and solvent. Gas in gas, like air, a uniform mix of oxygen and nitrogen. Gas in liquid, think of carbon dioxide dissolved in soft drinks. Gas in solid, hydrogen gas trapped in palladium metal. Liquid in gas, example, chloroform vapor dispersed in nitrogen gas. Liquid in liquid, like ethanol and water blending seamlessly. Liquid in solid, seen in amalgams such as mercury with sodium. Solid in gas, camphor vapor diffusing in air. Solid in liquid, glucose dissolved in water, a common solution. Solid in solid, alloys like brass, a mix of copper and zinc. Despite the different states, what defines a solution is its uniform composition, a single phase where components blend completely. Solutions can also be classified as aqueous or non-aqueous based on the solvent. If the solvent is water, the solution is called an aqueous solution, like sugar dissolved in water. If the solvent is something other than water, such as alcohol or ether, it is called a non-aqueous solution, for example, iodine dissolved in alcohol. Now let's look at classification based on the amount of solute dissolved in the solvent. An unsaturated solution can still dissolve more solute at a given temperature. Think of a mild vinegar solution. A saturated solution has dissolved as much solute as it can at that temperature. Any additional solute won't dissolve. A supersaturated solution contains more solute than it should theoretically hold. It's unstable and the excess can crystallize out suddenly. A classic example is a hot solution of sodium acetate which crystallizes when disturbed. Here's another way to categorize solutions: by how much solute is present relative to the solvent. A dilute solution has a small amount of solute in a large volume of solvent. For example, lightly salted water. A concentrated solution contains a large amount of solute in a relatively small amount of solvent, like strong tea or orange juice concentrate. These terms are qualitative, but they're useful for quick comparisons. From biology and medicine, we borrow terms like hypertonic solutions. These have a higher solute concentration than the fluid inside cells. They draw water out of the cells. Think of concentrated saline. Hypotonic solutions. Lower solute concentration. Water flows into the cells. Distilled water is a good example. Isotonic solutions. Equal solute concentration on both sides, like the 0.9% sodium chloride solution used in IV drips. Based on how many substances are mixed, we get binary solutions made of two components. Example, salt in water. Ternary solutions, three components, such as salt, sugar, and water in homemade ORS. Quaternary solutions, four components, like lemon juice made from lemon, sugar, salt, and water. The more components, the more complex the chemistry becomes.
One last distinction to make. Homogeneous solutions are what we've discussed so far. Clear, uniform mixtures with only one visible phase. Heterogeneous mixtures are not true solutions. They have visible separation, like oil floating on water or sand in water. Only homogeneous mixtures qualify as true solutions in chemistry.
Let's wrap it up. A solution is a homogeneous mixture of solute and solvent. We classify solutions by physical state, solute concentration, solvent type, number of components, and even their biological effects. From alloys and soda to medicine and seawater, solutions are central to life and science. In our next video, we'll learn how to quantitatively express the concentration of these solutions, using molarity, molality, mole fraction, and more.